Alina, our routine check. Can you please say something?
Hi, everyone.
Perfect. And click something.
OK. So I did.
Is it clicking?
Yes.
Is it clicking, but nothing changes? Let me see. Oh, they are completely different.
Yes.
Actually, please switch the screens and speaker console to show the same as the laptop that we just tested 5 minutes ago. Yes, it is, and the stage is yours.
Thank you very much. So, hi, everyone. My name is Alina Dima. I'm a senior developer advocate for Amazon Web Services in the IoT service team. And I'm really happy and excited to be here today to speak about how to move past prototypes and build resilience at scale in your IoT applications. Yeah, so as an agenda, we're going to have a brief introduction round where I'm going to introduce myself. Then we're going to speak about IoT and MQTT and a little introduction into AWS IoT. We're going to answer the question of why resilience is important in IoT applications and why we care about it. And together we're going to be building a maturity model for resilient IoT applications at scale. Then we're going to have a short conclusion and a sum up, and I'm going to open it up for your questions. So let's get started. Like I said, my name is Alina. I'm originally from Romania. I've lived in Germany for about 20 years. And I'm a senior developer advocate at AWS. So you might be wondering what that means. Well, I've got engineering experience, so I've been an engineer for about 20 years. And now I'm working very closely with the developer communities, so with engineers like you all, trying to help them build better and faster with IoT services and with AWS IoT. At the same time, I'm working closely with product managers from the AWS IoT service teams and with engineering managers and engineers, trying to build better products for you all. So let's look at the goals of this session. So first of all, this session is not going to be a comparison between tools and services. I'm going to use some AWS examples to exemplify certain problems that we're going to be talking about. But my main goal here today is to make you all understand what the challenges in IoT solutions are, and to understand how in IoT, in your solution, you can have data loss, how you can have data inaccuracy, how you can have delays in data, all because of sometimes internal factors, sometimes external factors that are outside of your control as an engineer. So then I'm going to help you, hopefully, make informed decisions about how to mitigate these challenges and also identify which tools you can potentially use to mitigate the challenges and how to build a maturity model. Now, the maturity model is going to help you when you are starting building an IoT solution to sort of know and be aware of the problems and of the steps that will help you build reliability and resilience. So we're going to discuss resilience as a crucial factor for data reliability in IoT applications. Yeah, let's get started. Let's get going. How many of you have worked with IoT before and know about MQTT in the room? OK. All right. What about AWS and AWS IoT? Anybody? OK. All right, very good. I mean, I'm going to do a brief introduction. So IoT and the Internet of Things is gaining more and more popularity. So billions of devices are already connected or will be connected in the near future to the Internet. And IoT generally is much more than a buzzword. So it is a means to an end. So it's not just technology for technology's sake. It's technology in order to drive improvements in processes that in the past were somehow a dream, right? So it is about using data insights that comes from machines, which were before like black boxes to us, and using those insights to, for example, improve efficiency in factories, or even improve your own experience in your own home, if you so wish. So this data generally can be an organizational asset, but only if it is reliable. So if data is missing, or if it's not transmitted with the correct SLAs, then definitely you cannot count on it to drive your business insights, right? So it is not possible to have reliable data in a non-resilient application. And this is one of the reasons why we need to build resilience in our applications. So MQTT is a messaging protocol very commonly used in the Internet of Things. So it is an application-level protocol, message ordering methods, and it's built on top of TCP/IP. So generally, we call it a lightweight protocol because the messages are generally very small. You have 2 bytes for the message header, and then you have the message body as well. So it enables bidirectional communication between what we call subscribers and publishers, all orchestrated by an MQTT broker. So publishers and subscribers don't need to know of each other in order to function. So if a publisher publishes data, it doesn't really matter for the publisher. I mean, of course, the publisher would wish that the subscriber is around and on and listening for that data, but it doesn't have to do so in order for MQTT to function. Generally, what happens is that the MQTT broker would discard any messages that are published on an MQTT topic if the subscriber for that particular topic is not present. So MQTT as a protocol is very interesting because it is supposed to introduce reliability in unreliable networks. So don't be surprised if in my talk you're going to hear a lot about default resilience of the MQTT protocol. Right, so AWS IoT represents the set of technologies around enabling devices like powerful edge gateways or sensors or actuators to connect to IoT core and to thus enable communication between those devices and data transfer with the cloud. So the main service, which is like the gateway into AWS, is called AWS IoT Core. It is a managed service, and it includes, among other services, also an MQTT broker. So devices would connect over MQTT, over a secure connection, mutual TLS-based, with a unique certificate and a unique private key to AWS IoT Core, and then they would send the data potentially for downstream services to process that data, like AWS Lambda, Amazon DynamoDB, or other AWS and Amazon services. Now, this data is going to be made available to different consumers based on whatever the consumer needs are. So it could be dashboards, or it could be, I don't know, some historical visualizations, or it could be mobile applications over any kind of APIs, be it WebSockets or HTTP. Right, so you might wonder, what are the challenges in building an IoT solution? Well, first of all, I hope you actually see my little maze diagram. So this just wants to say that IoT is not a straightforward line. So it's not like you start a prototype and then you get to production and it's all kind of a straight line. You are actually, as a developer in IoT, you are part of an ecosystem. Now, this ecosystem has multiple different components, be it hardware, be it firmware, be it network protocols, be it different communication protocols that are at application level, and so on and so forth, let alone the cloud side of the equation where cloud engineers build scalable solutions. And of course, if you are building a data application and you're looking to retrieve data insights, then you've also got the data analysts and data scientists and so on. So because of all these moving parts, and you as a developer being part of this ecosystem, there is complexity. There is a lot of need for communication, for open API specs, for SLA definition, and so on. Also the fact that the devices themselves are so different, so anything can be an IoT device, literally. I mean, you can take a mobile phone, or you can take a little microprocessor, or you can take a sensor that's used in agriculture. They're all IoT devices. And of course, based on their power and CPU and memory usage capabilities and so on, there are a lot of constraints that you need to deal with as an engineer based on your use case and on your solution. So getting started and moving past prototypes isn't always very easy. There are so many standards out there, and every time a standard needs an improvement, then a new standard is born, and so on and so forth. So in addition to all of this, problems are hard to identify. So usually, of course, you have QA, and the QA tests in a lab or in some sort of simulated environment. But of course, when you ship your devices out there and they are with customers, suddenly the problem space totally changes, and you start seeing issues, especially connectivity issues, or maybe even issues with your hardware and software that you have not seen before. Right, so identifying problems early enough is very important, and this is why we're going to talk later on about observability. The The shared responsibility model is crucial. And here I'm not talking about the cloud provider versus your responsibility as an application developer. It is more even within different teams who are building the same solution. So you've got the embedded engineers or the edge engineers working together with the cloud solution engineers, working together with a data scientist. And of course, when something doesn't work, there is a little bit of finger pointing going on, where is the problem, and so on and so forth. Right, so why do we care about resilience in IoT solutions? Let's look at the real-world example. And this is a project that I've been working on, I think about 5 years ago, so it's something really dear to my heart. We're going to be looking at an elevator company. So this elevator company is trying to build a digital solution to monitor elevator activity. So their main goal is to ensure that they can get enough data from the elevator to be able to predict failures and to auto-schedule some maintenance windows. So they figured that it is actually quite expensive to send technicians to the elevator after the fact, right? So if people get stuck in lifts, which is horrible, I don't wish that on anybody, but if they do, then technicians need to come. And then they need to identify what the problem is, then they need to go back, and then they need to bring the components that they need to fix this elevator, and so on. So this is costly. So it would be nice to actually know before a lift breaks down that it is close to breaking down, so you can schedule a maintenance window. So information that could be useful would be, for example, door openings, door closings, and how fast the door opens and closes, because it might be that the door sensor is a little old, and this means that the door would take actually longer to open and longer to close, thus saying that maybe you need to replace that door sensor. The speed of movement is also very important, and it can also indicate some problems with the motor or some other problems. Also, something important and interesting could be a lift run, right? So this is how long it takes a lift to leave from the target floor, from the current floor to the target floor. And once it arrives at the target floor, so at the destination floor, then you can report things like speed, all the floors that has passed, how long it actually took to go from one floor to another without stopping, and so on. So all this would be interesting. So we've got a bunch of teams building this solution, and they've done an MVP, and now they're actually on production with this solution. So I mean, this is something that actually really happened, so it is an anecdote based on a real fact. So on production, it turns out that the solution does not meet the requirements. So what happens is that devices go offline and either stay offline, or they go offline and come online very often. So they fluctuate between offline and offline. Then what happens also is that data is missing, or is inaccurate, or marked inaccurate by the data engineering teams. So what happens is that more door openings than door closings are being reported, or some floor information is missing. So this makes it really difficult to be able to actually tell, is it a problem with the lift, or is it a problem with the solution? Where does the problem lie? And so the different teams can't really tell, because they don't really know how much data is missing, where the data is missing from. They can't actually tell where the problem lies. If we look at the high-level architecture, it's actually, it's a simplistic view. So on the downside of the diagram, you actually see what's happening on the edge device. So you've got an application with different business logic pieces and an MQTT client. Now, this MQTT client is actually connecting to AWS IoT Core over mutual TLS. And then once the connection is successful, it starts sending data on an IoT topic. Now, the rules engine, which is the service that directs and forwards the data to different downstream services, is picking up the messages from this topic and pushing the messages into Amazon OpenSearch. Also, as a backup, some of the raw data, actually not some of the raw data, but all the raw data should ideally be stored into Amazon S3 and processed by other systems and other components. Right, so this is the high-level architecture. Now we're going to look at what can go wrong with that architecture. So what can happen is that the communication between the MQTT client that resides on the device and the application, the cloud side of the application, can be lost. So this connection loss can be because, imagine that this device that is at the edge is connected to the lift controller, which is connected to the CAN bus, and the device is using cellular networks for connectivity. So if the lift is moving underground for the parking garages, then it can lose connectivity, so this can actually happen. If the elevator is in a building in some weird direction, weird location, then it could be that the network operator doesn't have very good performance there. So there can be multiple different reasons, but the loss of connectivity or unstable connectivity can cascade into weird behavior, right? So if the MQTT client doesn't manage this loss of connectivity and attempt to reconnect, then data can be lost, right? So messages are simply not sent. If messages aren't sent, then they are definitely not arriving on the cloud side, which basically means that the rule engine can't pick them up. What can also happen is that because of different software issues, the data is not ingested successfully into Amazon OpenSearch. So what happens then, right? So, or if the write operations fail to Amazon S3, what happens in that case? And of course, this architecture doesn't really have a component that contributes to observability or a component that talks about data consistency. So if these teams of engineers are being asked, where is the data, how much data are we losing, they wouldn't really be able to tell on a first glance because they have no consistency check. So they don't check for data completeness and consistency. And also what happens at scale is that all these different issues cascade into undeterministic behavior. So how do we solve these issues? Well, generally, we try to solve reliability issues by building in resilience. And now we're going to look at how we can build in resilience on a leveled maturity model type of way. So the first thing we're going to start with is the resilience of the MQTT connection. And remember how I was telling you that MQTT has some resilience features which are built into the protocol itself. Well, engineers just have to use those features. Right, so the keep alive is more or less like a heartbeat between the publishers and the broker and the subscribers and the broker. So in a client-server architecture, it's more or less like a ping to make sure that the connection is alive. So the client needs to make sure that it configures this ping timeout in such a way that the server side, which is the broker, would actually understand that the connection is lost in case that there are some problems. The client takeover also ensures that no two connections can exist on the broker side at the same time. So if a connection with the same client ID is attempted, then the broker will kick the previous connection out and disconnect it and ensure that the new connection remains active. Last will testament is about the last message that a device would actually send for its subscribers when it ungracefully disconnects. So that helps downstream services know more information about the last state of the device. And persistent sessions is a really important feature because it allows, in a really fast way, for the clients to reconnect when they drop connection. Because the server side, so the broker, would actually send the same connection because it has persisted it. So the client will not open a new session, but it will receive back the existing session with the existing subscriptions and so on. So this makes the entire communication connection handshake a little faster. And it could be really useful in case of temporary connectivity losses. But of course, this is not enough. So it's nice that MQTT has all of this, but ideally, you would also make sure that you build resilience in your application. So the most important thing, probably, is to understand your MQTT client. So there are many libraries out there that you can use, starting from different open source libraries, or Paho client, or Mosquito client, or the AWS IoT SDK, or you can go something higher level like AWS Greengrass. So it's your choice. But you have to know that sometimes the default settings of all these clients are different, right? So you need to make sure that you understand how your client works, so you know how you configure the keep alive, how you can give a client ID to your MQTT client, and so on. Managing the MQTT connection lifecycle is also a really important thing. So this is more of a design decision that you need to be conscious about when you're architecting an edge IoT application. So ideally, you would encapsulate your MQTT client connection so that you have control over its life cycle. So this means that you can, once you have this encapsulated, you can create the connection, you can configure the connection, you can run the connection, check its status, and disconnect the connection if there is a problem, without needing to modify many places in your application. Because MQTT is an event-driven protocol, all these events have callbacks, right? So when you are sending a connect event, then you're going to receive a callback, which is similar to a connection acknowledgement. So you need to listen for these callbacks and make sure that you store the state of your connection and the health of your connection so that you are constantly aware of what's happening. So for example, for your use case, you might not want to publish data if your MQTT connection is not up and running, because that would make no sense. On the other hand, you actually might want to publish data, and you might want to buffer this data. So this is all behavior that you would need to build based on your needs. Another important aspect is making sure that your devices actually know what the time is. I mean, I know it sounds trivial, but many of the cheap IoT devices actually don't have a real-time clock. So what happens is that you need to build an NTP client and make sure that the devices are aware of what the time is. If they are not aware of what the time is, then the validation of the server certificate might fail, in which case, with AWS IoT, the devices will not be able to connect successfully, so there will be an authorization error. There are tools out there that help you test your MQTT connection during your test phases. So what these tools can do is simulate different kind of network conditions like unreliable networks and so on. So one such tool is called AWS IoT Core Device Advisor. So you can use Device Advisor, configure your devices with a test endpoint for Device Advisor, and let the cloud side run a suite of tests to validate the way you've implemented your MQTT connection and publishing and so on. So this could be something useful for troubleshooting and for early stages in your development. Now, message delivery can also be important for your application. So quality of service, probably all of you know about this. So this is around reliably sending data. So is it a fire and forget, which is the quality of service 0? Or do you want an acknowledgement from the broker that it has received the data? Or do you want that you send the data once and the broker receives it once and only once? So these are all decisions that you might want to make. Message queuing is something that goes very well hand in hand with persistent sessions enabled by MQTT. So this means that your client might buffer the data in memory if you open the persistent session. Again, I'm saying might because different client libraries just behave differently, so you need to understand how much and for how long this data will be buffered. So that's something usually the documentation of the client tells you, and you don't have to look in the code. So additionally, again, important, manage your MQTT transport layer. What you don't want is that your domain model level in your IoT application starts dealing with low-level connectivity issues. So you want to assume when you are at a higher layer in your architecture that the connectivity issues are managed below. You can have a software layer in between that maybe queues messages or maybe checks for subscriptions and so on. Tracking success and failure for your data delivery could be very important if you care about data consistency. And when I say if you care, it actually matters because you might be delivering, your solution might want a dashboard for alerting, for example. So only real-time data matters. So if only real-time data matters, why do you care about storing or caching or resending? Then you can just publish with QoS 0 and forget about it. But it could also be that you care about eventual data consistency. So like the elevator, when it goes on the lower floors, you might want to send data later with a correct timestamp and server-side make sure that you're ingesting it at the right location in the index in Amazon OpenSearch. So make sure you understand your requirements and based on that, decide whether you want to build offline data storage or not. So it's important if you care about data consistency not to rely just on the buffering that happens in memory. Because if your application crashes or your operating system reboots and so on, if there is a power cut, it's possible that you lose all that data because it is just in memory. So if you've managed all the connection and the publishing lower levels, then the next step is your application runtime. Now, of course, based on the operating system that your application runs on, is it an embedded operating system? Is it a more powerful Linux? I would say it matters how you do it, but what you need to do might not be different, right? So you need to make sure that your application process is always up and running. No matter what happens with the operating system, that it reboots, no matter how many times your application crashes, as long as your application recovers from all these resilience problems, then you can still do something and you can still investigate and troubleshoot. If your application dies and is dead, or your device dies and is dead, then you can't really do anything about it. So you end up going with a USB stick or going there and doing a hard reboot. So this is kind of what we want to try and avoid. Using a process management tool just makes your life easier. I mean, Docker is an example of this. You can also use PM2, and I'm sure there are other process management tools out there. Graceful exits in your application are quite important. So normally the operating system would signal if there will be a shutdown of your application process. You can listen for the signals and you can be graceful about it in your application. So you can disconnect gracefully the MQTT connection so the broker on the other side knows that it was a relatively clean disconnect, and you can also flush all your data to the local storage and so on. So there are things you can do. And of course you need to log. So application logs and metrics like CPU usage, memory usage, and so on are very important. You might also want to keep track of how often your application crashed and rebooted, just to know for observability purposes. But of course, application logs are not just important when something doesn't work. So it's not just about troubleshooting, it's just about knowing that it actually is working and having that guarantee. If you're dealing with data and you've got in your end solution data producers and data consumers, it is important to define data contracts. So data contracts are just agreements between the data producers and the data consumers as to how the data would look like, what are the SLAs, what are the keys, what are the values, the potential values for your data. So this is all really important. Also, it's important for your data consumers to understand what the latency expectations for your data transfer are. And also they need to understand what the reporting interval is, right? Because maybe the sampling interval, imagine a temperature sensor. It can have a sampling interval of 1 second, but you might not want to send these values. So the reporting interval might actually need to be different. Don't send raw data unless your consumers need it. So I mean, imagine the CAN bus situation, right? So the edge device is connected to the CAN bus of the lift. You don't really want to send binary data because your consumers would not understand it. So you need to build your domain model, ideally validate your application domain, and ideally validate in code. So you have events and metrics and activity all validated in code. When it comes to data integrity, I think here it's a little trickier because you need to figure out whether you need it, whether you want to build it, and craft how it would look like. So if you care about data consistency, do implement checksums for your messages. Do put timestamps on your messages that go from the devices. And fill in the data gaps. So with OpenSearch, you can actually fill in the data gaps, and it is no problem at all as long as your device sends a timestamp. Logging, monitoring, and alerting is also extremely important. And now we are coming to the most interesting part. Remember that architecture diagram where we spoke about points of failure and what can go wrong? So what happens when something goes wrong? So the first step is to identify and ask yourself the question, once you've architected something, what happens if this component fails, right? And then you need to manage the point of failure literally with fallbacks, right? If you're calling external systems in your IoT solution, be gentle with those systems. I mean, they have SLAs, and some of them might not be running in the cloud, so it is important that you don't hammer them with requests and that you respect the SLA and the TPS dictated by the SLA. Build retries with back-off strategies. And if you can, pick the highest level of abstraction. I mean, this is a concept that I actually like. If a managed service can do the job for me, and if actually this job is not part of the core competency of my solution, then why not use it? Of course, if it's not a technical fit, then you just go for something else, and maybe you build something yourself from scratch. And then if you can see it, then you can fix it. So having the visibility as to what is going wrong in your application is very important. Now, standardized and centralized logging for your application is sometimes something that comes in as a non-functional requirement. And we all know as engineers what happens with the non-functional requirements. We just build them on the side, or we build them later. But if you don't have standardized logging, then an operations team somewhere is not going to be able to troubleshoot. And then you're going to start getting tickets that actually belong to a different team, but they arrive in your plate because just the logging is just not correct. Tracing and metrics, checking performance, checking latency are also important. And of course, if something does not meet your threshold, then you should trigger an alarm. But that alarm should actually go to the right team, and it should be, for real when something is really broken. So the false positives are not really nice to have in an IoT application. So if you have the IoT solution, what you need to do is scale every single step and make sure that it actually works at scale, right? So make sure that the part of your application that receives the data can scale up to millions of devices sending that data. Make sure that you can scale with different frequencies and different reporting intervals, and use services that fan out, right? So such examples with AWS could be SQS queues, it could be SNS, it could be Amazon Kinesis data streams or Amazon Kinesis Firehose. Retries are very important with the backoff strategy generally, or you can do jitters. Also decouple your different services. If something goes wrong, you don't want to propagate that error throughout your application. So microservice architecture or decoupling the different components is very important. Error handling and observability with logging, metrics, and tracing. Right, so now, if we remember our original architecture with the problems that can occur, let's see how we could fix these problems, right? So the first step was about connection loss. So if your MQTT client is resilient and your application is managing the MQTT connection and the publishing of messages correctly, then your client will recover in terms of these failures, right? So we talked about decoupling, right? So the point of failure that we saw before from the rule engine into Amazon OpenSearch, we have now fixed by using Amazon Kinesis data stream, which can literally first of all, scale, but also store these different records for 24 hours even, and then we can ingest them in batches into Amazon OpenSearch. Now, of course, if we use Kinesis Firehose, then there is a retry strategy and the batch ingest, and we can also put a failure rule for the data that doesn't get successfully ingested into OpenSearch to go into Amazon S3. So once we see data in S3, we know that the insert into Amazon OpenSearch has failed. So then we can go through that data and we can build a parallel path to ingest it, right? In the same way, in the rule engine, we can actually set up an error action. So with this error action, if the success path did not happen, then the failed path would kick in. So the data will be in S3. Right, and observability. I mean, here is the example of AWS services, right? But in the same way, other cloud providers and also you potentially building in-house solutions can also, build this. You just need to be aware that it has to be there. So logging with CloudWatch is an example. You can put CloudWatch insights on top of that and run queries. You can use Amazon X-Ray for tracing and for performance evaluation. Device Defender is an interesting service for IoT because it helps you see metrics like number of devices being currently connected or disconnected, the reasons for disconnects, and so on. Fleet Hub is just a user interface, and it gives you visibility into your fleet, and Device Advisor we already spoke about. Right, so the maturity model for IoT solutions looks a little bit like this. I mean, this was at least my interpretation of it. So it's quite a bumpy road. You go from a spike that works on one device, and then you hope that everything is working by building some MQTT resilience in there, by configuring the client. And then you know it's working because you've built some observability, you've built some offline data caching, and you've handled the acknowledgements from the broker on data publishing. So that's around 100 of devices. Then you're mitigating what goes wrong, and mitigation is about points of failure and implementing fallbacks, so now you're sure that it actually works. And then comes the point of being ready for large scale. So this is, if you're working with AWS, you need to model your load. You need to make sure that you create tickets to the service teams in case you want increases in the limits. Because yeah, guess what? I mean, we're dealing with serverless technology sometimes and with managed services. But if the load is too high, then you still need to increase the service limits, which are officially in the documentation. For that, you need to do some modeling yourself. Yeah, and then it's basically practicing. It's basically looking at the logs, having an operations team, and this is a summary. I'm not going to go through this again. This is more for you guys offline once you receive the slides to have a look. So it summarizes pretty much my talk, it's available for you offline. So what are the key takeaways from my session? Well, IoT is a bumpy road. It's more like a maze, and you are operating in an ecosystem if you're working in IoT. Resilience is the mechanism to build reliability in your application. External factors are very common in IoT solutions. So you don't control what your network provider does. If there is some sort of outage, you have no control over that. If your devices don't recover after a network outage, then that's totally your problem. You need to think about that in terms of building more reliability in your application. resilience must be built in, and this maturity model can be used. The fact that you saw it as a step-by-step approach does not necessarily mean that it is sequential. So you might need to think about points of failure at early stages in your production readiness design and architecture. Right, and a bunch of resources that actually I believe are really relevant for you to have a look at. One of them is a dev.to organization where me and my team are writing blogs. So if you scan that QR code, you will actually end up in that dev.to organization, so you can read our blogs and find out more information. We are writing not just about IoT, connectivity, MQTT, MQTT clients. We're also writing about FreeRTOS. We are writing about Greengrass, and we're doing early prototype kind of work, but also production readiness and information about operations and scale. And we have a YouTube channel as well, so there is a link to the YouTube channel. You can subscribe to our videos. Right, and as a last step, everyone loves feedback, and I love feedback as well. So please feel free to rate this session, and yeah, let me and the organizers know that you're having a great time at the conference, just like I am and like everyone is. So thank you very much, and now I'm going to open it for questions.
Applause, please. And for you, it will be our usual task to no, A is never pronounced as A. Task. To choose the best question that we will give some prize that can be offline or online questions. So, our first question and the first pretender to be the best questions of this talk, you're welcome.
Thank you, Alina, for the presentation. I really liked how you construct the slides and deliver the information. So my question is one of the aspects on reliability of the ecosystem. Mostly it's about the guaranteed natural order of the messages delivered from the publisher to the subscriber. You mentioned about external factors which could affect the even guaranteed delivery, moreover the guaranteed order, like natural order of the events which we are interested. So what do you suggest on how to support in such ecosystems the guaranteed order where my subscriber is heavily interested in that? Maybe one of the possible solutions can be the buffering on the client side, on sorting on the client side. In that case, we will have some latency in real time or close to real time applications. So I would like to listen your inputs. Thank you.
Yeah, of course. So the ordering of the messages, if you put a timestamp and potentially an ID that you increase when you're sending the data from the edge, generally, depending what your subscriber is, right? So if your subscriber is a service like Amazon OpenSearch, or if you're going, for example, from a Lambda function to Amazon OpenSearch, the timestamp will make sure that your data gets ingested at the exact right location in your index. Right, so then when you're searching through your documents in OpenSearch, you have the ordering guaranteed. But of course, if you are doing some other kind of processing, then you might need to look at the timestamp and examine the timestamp yourself in your application on the cloud side. I mean, it's not enough to queue the data and buffer it and ship it over MQTT, because there are network delays that can affect how your data gets delivered. So you do need to build this up in your application based on what your downstream service is.
Well, next question, please.
Hello, and want to do with situation when there is too enormously time without connection, and device should store a lot of data, enormously a lot of data before the connection is restored, and you can send it with a batch from the booth and so on. And what is if the data is especially important and you can't wipe it, and you should store it on a mobile device and it's too hard for it? Or what to do in such situation?
Right, so in the situation where you need that the data is consistent and you have long periods of time of your device being disconnected, then local storage is probably the best idea. So you can think about an edge database that you could use.
If it's mobile devices of usual customers and you can't store a couple of hundreds of megabytes on mobile phone, customers could throw you away with such mobile application.
Yeah, so if it is your mobile device that actually sends the data, then you might need to potentially consider a different architecture that would actually involve that a different backend system might deal with this data. So without storage at edge, it depends for how long, right, we're talking about. So if it's days or weeks,
Maybe
then
15 minutes, but it's mobile
okay.
game or something like Red Hail system. It's a lot of logs in it, and even in 15 minutes, it could be a couple of hundreds of megabytes.
Right, and you think that in memory is not enough, because if you use persistent sessions, you can store. It's not unlimited, right? Because it's always dependent on the operating system, memory constraints, and so on. But you could still, with persistent sessions, store the data in memory, and then when the device recovers, you could send this data, ship this data.
Okay, thanks.
It is a dark trick known as graceful degradation, where you store a little bit of data, and if you still can send it, you start to average data, store more data with less precision. If you still can send and store even more data with moving average with less precision, and after, I don't know, few days of offline access, you will have just like 100 kilobytes with average data instead of a few hundred megabytes of precise data. But use with caution. It's a dark trick that can lead to unpredictable results.
Yeah, I mean, you can look at the reporting interval as well versus the sampling and report less, if that makes sense for your application. Report less often.
Please, next question.
Yeah, thank you for the presentation. And nowadays, in software engineering, we are very used to, with all this agile methodology, to somehow make an MVP, prove the concept, and then scale. Of course, that is hard when we have to deal with hardware, with IoT devices, but still, sometimes business forces us to do that. And in this case, it's a problem when we can, in the beginning, we can have devices much simpler with different capacity properties, and later we can scale, make all these devices which are serving almost the same problem, trying to solve the same problem, but a little bit different devices, but still on the server side, we want to have not that complicated system. Are we here forced to have multiple, let's call, servers will serve all these different versions of devices? Or if not, it can be another single point of failure, right? When we have different kind of devices, with different capacities, but on the backend side, we need to somehow deal with all these different devices. What steps can we take here to be on the safe side?
Right. So first of all, I think that the cloud side of your application should, of course, store information about your different edge devices, right? But it should not matter what kind of devices you have at edge, right? So what you need to do is make sure that you have a domain model that no matter what your hardware is, no matter what type of device it is, right? So with elevators, it would be, is it a Schindler elevator, is it a ThyssenKrupp, and so on. It doesn't really matter what kind of controller it's connected to, what kind of device you have. As long as you have your domain model and your cloud application understands that domain model and knows the domain model, it does not need to know about the ins and outs of your device, right? So if your device connects via serial or it connects via CAN bus, if it's using cellular networks or it's using, I don't know, Ethernet or Wi-Fi, it should not matter for the cloud side of your application. So it shouldn't be a point of failure on the cloud side, the fact that you have multiple devices. However, when you're doing the MVP, make sure that you do an MVP with all these devices, right, different devices. Because it could be that your edge application, if it runs on one device of one type, on one hardware, it might not run, it might need modifications to run on other devices, right? So you need to make sure that all these different types of devices are tested properly at MBB level and that you have test phases for all of them. But on the cloud side, ideally, your domain model would be abstracted and your cloud side would not. Of course, you need to scale it up. The more devices you have, you need to scale up. Ideally, you would also store the model of the device and so on, so you know the kind of data you are dealing with and where it's coming from. Does that answer your question? Sure.
Actually, you can discuss more in the discussion zone. And for here, we have a little bit of time. Are there hands to the left? Nope. In the middle? Nope. I have one question of my own, actually. There are more than 200 services in Amazon Web Services. How do you remember all the names?
Well, so the answer to this question is I don't remember all their names. The services that I'm working with in IoT and serverless technologies mostly, I know all their names. And I also know if they're Amazon services or AWS services, because this also matters. But for the other services, and if I encounter a service that I don't know, I simply look in the documentation for it, and I also try to remember the name for the next time.
Thank you, and please one more round of applause to our speaker. And now the hardest task for every speaker. Which question is the best one?
Well, I will give this prize to the question which was the most controversial and not easy to answer, and that's the question about the mobile storage and the data and how you deal with mobile apps being disconnected.
Please go to the stage, and we have. And we have a special prize this time, which has a size. You can go to our assistants to change it if needed. Please, can you gift our prize? And one more round of applause. Thank you, thank you.